So our last speaker today is Purna Sarkar from UT Austin.
Thanks, Ben. Thanks to the organizers for inviting me. It has been really great fun, like Carl said. This is basically joint work with Boe Yan, who is also at UT Austin. Oh, and thanks to everyone for sticking around for the last talk of the session. That had to be said. Okay, so and this is Boe Yan. None of this would have been possible without her, right? So what I'm going to talk about today is covariates and semi-definite relaxations. And it's great that Dave actually talked about semi-definite relaxations a bit, but what I'm going to do, I think, is for some of you who haven't seen semi-definite relaxations of the block model, I'll kind of just talk about a vanilla block model just to give an idea about how a likelihood relaxation ends up looking like a semi-definite program. And then I'll talk about how we fold in covariates into that in a very simple way, some theoretical results, and finally, if time permits, simulated data and some real data experiments. Okay. All right, so if you weren't convinced about how important covariates were up until the beginning of the conference, now you should be, right? So I shouldn't be spending way too much time on the importance of covariates. Here is one particular example. This is actually a network built from Mexican politicians. There are about 35 nodes. It's a very small network, but it's very interesting. So there are two groups, the military and the civilians. Okay, and this was built from the connections of friendships and kinships, etc., and close working relations between different presidents. So here on the left, what you have is that graph. Red is, I think, red is military, and then blue is civilian. There are about like 13 military, and rest of them are all civilians. You also have covariates here. So the covariates are when they first came into power. And you can kind of see that if you look at the covariates, the military came into power sooner. So that already gives you kind of a nice understanding of who is what. And finally, this is just the adjacency matrix, and it tells you that they all kind of talk to each other quite a bit. Okay. So I just want to have, I want to talk about this because there are some nodes, very easy to see how covariates help in this example. So then there are some big arrows there, and those nodes are basically nodes which have equal number of connections to both groups. So if I just looked at the graph, I'll be very confused about how to label them. Yeah.
What's the definition of a connection?
It's basically, I'm just reading or remembering the description from the PIEC web page. It's friendship, kinship, and any kind of collaboration. Because apparently it turns out that all presidents up until a certain point used to be former secretaries in the last cabinet. So they worked with each other a lot. So it's kind of those relationships. So you can see those two nodes. They have equal number of connections to both groups. So you can't really tell much from the network. However, if you look at the covariates, you can actually see that some of them came to power sooner, some of them came to power later. And from that, you should be able to tell that these guys are military and these guys are civilian. Because what happened was after the revolution, mostly people were military, and then slowly they were replaced by the civilians.
What do you mean by sooner relative to what?
After the revolution.
Oh, after the
revolution. And the time here is, I think, after 1900 or something like that. It's number of years after 1900 when they came into power. So initially it was mostly military, and then they were replaced by civilians. So if you look at when they came into power, you get a fairly good idea of whether they're military or civilian.
But you have to adjust for their age, right? It's a pretty big span.
I don't think it's that big a span. I think here I have about maybe like 50 or 70 or 80 years. 80 years, yeah.
So that doesn't account for their age?
It doesn't, but let me think.
It's just the year they first took
power. Yeah, it's just the year when they first took power.
Relative to a fixed point?
Relative to like 1900, I think. Yeah. Okay. So, and in the same way, if you have some covariates which are kind of close to the transition where it's not clear whether they're military or civilian, you can look at the network and see which group they connect to more. So you can kind of see that there are complementary pieces of information here. Okay? Yeah.
In that middle graph, what's on the axis?
Oh, the axis is basically for all different politicians, so 35 politicians.
So
And I'm basically just, on the y-axis I have when they came into power. So you can see that there is, yeah, there is no axis really. I'm just plotting, for everyone I'm plotting when they came into power. Okay. So I don't need to really talk about this part. It's everyone already knows about it, right? But the one thing that I want to point out, I guess, to get into the semi-definite relaxation is we have a fixed and latent community membership matrix Z. It's n by r. I'm going to use r as number of communities, which is unfortunate because we used up k for something else. Yeah. So like Dave said, Z has every row of Z sums to 1, because at any point you can belong to exactly one community, 0 ones. And every column is basically telling you who all belongs to this particular cluster, and so they are going to sum to the size of that cluster. Let's say it's M1, M2 up until MR. And there is a R by R parameter matrix B, stochastic block model. And here is the thing that you have seen again and again, which says that if I give you 2 nodes and tell you which blocks they belong to, I can immediately tell you what's the probability of connection. So so here is kind of likelihood relaxation, and I think it's a cute thing, so I would like to talk about it a bit. A lot of research has been done on this. So if you look at the log likelihood, right, what is the log likelihood of a block model? You are essentially going over all pairs, figuring out which communities the 2 nodes belong to, and then picking that probability out of the block and adding some log of that based on whether there is an edge or not. So essentially what you are doing is you are adding all the pairs of the adjacency matrix. So that's why with some weights. So if I give you a very simple model, P within blocks, Q across blocks, R clusters all of equal size, then your log likelihood boils down to something very simple like this. Okay? So in the bracket what you have is log odds of P minus log odds of Q. P is within block probability of connecting, Q is across. And if that is large, then you know there is high separation. Oh, and the other thing is you also have this other term which ends up being a constant simply because you have equal sized clusters. So you can throw it away, and what you are left with is this particular optimization. Okay? And essentially all I'm saying is, well, trace of Z transpose A Z, Z is a binary matrix, is columns sum to n by r, its rows sum to 1, so on and so forth. And of course you can't really do anything about it, you have to relax it, and how you relax it is up to you and leads to different relaxations or different problems. So one way of relaxing it would be to say, I forget about everything else, I forget about it 0, 1 or even between 0 and 1, I'll just say that Z transpose Z is n by r times the identity. I could do that, right? I have exactly n by r blocks, n by r people in every block, so my Z transpose Z matrix is k by k with the diagonals as n by r 0 everywhere else. What does that give us? Even if it's horridly non-convex looking, it's eigenvectors, right? Top are eigenvectors. Okay, you could do that, and we have been looking at spectral clustering and eigenvectors for a while. Or you could do this nice nifty trick where you look at the trace, you say that, oh, trace of Z transpose A Z, can't I just move the Z transpose to the right? So now I have trace of A Z Z transpose, Z Z transpose is my new matrix. Okay, that's the one I'm going to learn. It's a clustering matrix. We'll call this X. X is positive semi-definite. All the elements are between 0 and 1. All the rows sum to n by r. Right, and the diagonals are all 1. So this gives you a semi-definite relaxation of a fairly horridly non-convex thing. Okay, and of course there are problems with SDPs, even if they are nice and provable and gives very good results, which I'll show. They take forever to run. And that's hopefully what next time around we will not have this problem. Okay. Okay. So that was the unbalanced case. In the balance, that was the balanced case. Everything was of equal size. Now let's say you have the unbalanced case. What do I do now? Right. So I had this X matrix, remember, which was the clustering matrix, where I had all ones. Within, if 2 people belong to the same cluster, I have 1, 0 otherwise. I take that matrix, I sum every row. What I get is basically n by r times 1. can't really do that anymore. If I have everyone belonging, every cluster having different number of things, I'll end up getting something like cluster sizes, and if I knew where to put down what cluster sizes, I would have solved my problem. So I can't really just use that. So it turns out there is a very simple way of dealing with it. You just use a normalized version of that X matrix. So what do I mean by that? This is my matrix. Let's say you have 2 blocks. Here, instead of having all ones, I'm going to have 1 over the cluster size here, 1. And here it will be 1 over M2. Right? There are M2 nodes here, M1 nodes here. If I do that again, take row sums, it's equal to 1. And then you can do all sorts of things with this. Everything kind of falls into place. You basically say that the trace of this is going to be equal to R, the number of blocks, in this case exactly 2, and so on and so forth. And this is kind of, there has been other works which looks at unbalanced clusters. So that's not very new. This one is actually easy to code up and runs pretty fast as well. Well, fast for SDPs. So Dave talked about assortativity and not being assortative, and I want to kind of go and make that very concrete. So I have 2 parameter matrices here. The right one, so white, very, very white means a very large number. Very dark means a very small number here. So this one is going to be called strongly assortative, where the diagonals are very much larger than the off diagonals. In particular, even the smallest guy among the diagonals are going to be the larger than the largest off diagonal guy. And this one is not like that. It's called weakly assortative, for which really nice results were obtained by actually people who are in this room, Arash and Lisa. And here what you say is, well, for every block, the probability of connecting inside is bigger than the connecting to other blocks. Okay, so for example, however, it's not strongly assortative. For example, here you have a higher number than everyone else, but you have a lower number than that guy right there. Okay, so this is not strongly assortative, and it gives you a much broader range, like Arash showed. And I'm going to call pk as for every k the diagonal probability, and qk will be the off diagonal, the largest off diagonal probability, and all the bounds will have essentially pk minus qk. Okay, so just a very short review of what has been shown for semi-definite relaxations. But before going into that, how do I measure consistency? Well, x hat is what you get out of the SDP. X0 is your version of the truth. It could be a normalized thing, or it could be what Arash had before. And essentially, it's just a multiplicative error. Take x hat minus x0, take the norm, divide by norm of x0. In the dense case, actually, up until about, I think, 14, all the results were for strongly assortative cases. Right? You basically showed that that error either goes to 0 with high probability or is 0 with high probability. Right? And for the sparse case in the strongly assortative setting, I think Dave actually mentioned that paper. It's Guedon and Vashinin. They had this nice Grothendieck inequality that they used, and they basically showed that they cannot show consistent, of course, because by now we all know that everything goes wrong in the sparse case. So what they show is the error is going to be a small constant, and that's often fairly nice. Even if it's not going to 0, it's a constant. And weakly assortative was actually, for the dense case, was done by Lisa and Arash, who is right here, and a kind of natural byproduct of the analysis completes this somewhat. So even for the sparse case, you can have weak assortativity. Okay, so let's now get to covariates. How much time do I have? Oh, okay. Don't do that. Okay, so covariates, right? So I think Arash talked about covariates before, and I'm going to take the simplest possible model just to kind of look at the likelihood relaxation for this. Mixture of Gaussians, what can be simpler than that, right? So before you had stochastic equivalence for covariates, now we will basically say that, well, if you are belonging to cluster 1, then you have a mean that is mu1. And let's say for now, we are not going to have this for the final results. Everyone has the same variance sigma square. Okay? So if you do this, of course it's a Gaussian, and it was Gaussian because the log likelihood looks nice under this. You write down the log likelihood just for the covariates. It's this nice little thing that again has this quadratic form. Sorry. You look at the mu, those are the parameters, and you do the typical trick that you do in profile likelihood. You just say that I'm going to replace the mu by the MLE, right? Because the mu's are basically just cluster centers given the cluster memberships. And if you do that, you end up with, again, another thing that we have seen before. Something like trace of, before you had trace of A and ZZ transpose, and now you have trace of YY transpose times ZZ transpose, right? And that immediately is kind of telling you that, oh, before A was the similarity, and now YY transpose is the similarity, okay? And now that A and Y are conditionally independent given Z, the log likelihood is going to become this. Very nice, right? So A plus lambda YY transpose and ZZ transpose, trace of that. Oh, great. So, and the lambda in this particular case boils down to something like this, so a ratio. If you look at the top part of the ratio, it basically is talking about how separable the data is in the covariates, right? If sigma is small, it's more separable, so the numerator becomes large. And this one is basically the log odds of P minus log odds of Q that I talked about. Things are very well separated in the graph. So the moment you see that, you get all happy and you glow inside, because that gives you a way of tuning things, but it's all wrong, because in general you won't have the right P, right Q, all the things won't be P, all the things won't be Q, you won't know sigma square, and on top of that all the sigma squares, even if you had a Gaussian model, won't be equal, right? So then we thought, you know what, that's enough of modeling, we are going to just treat it as an optimization, okay? So if you do that, if you try to phrase it as an optimization problem, it's also interesting that this part right here is none other than a k-means penalty, right? Because k-means looks very much like Gaussian likelihoods when you have the same sigma squares everywhere. Okay, so it's basically just log likelihood plus a k-means penalty. Okay, and so I take that, I do a spectral relaxation like I talked about before, we get Karl's algorithm, well, a variant of it because you have Laplacians, which is nice because you take the adjacency matrix, you throw in some similarity derived by the Gram matrix from the covariates, you put them together with some tuning parameter, you get eigenvectors of that. Or you can do SDP relaxation of this, right? Just like before we were doing SDP relaxation of A, you could do it like this. Or you could basically replace the YY transpose because we have really left the modeling, so why not get what you can, throw in a kernel there. Throw in the kernel similarity matrix, n by n kernel similarity matrix of the points which is derived from the covariates. You can use a Gaussian kernel, for example. So now I have this, I'm going to call it SDP combined or SDP comp, and if I make A to be the all zeros matrix, I end up getting something which is none other than kernel k-means. So you are not doing k-means anymore. So I mean k-means can also be solved using SDPs essentially. And if you do that, you are not doing k-means on the covariates, you are doing it in the kernel space. That gives you kernel k-means. And on here it just gives you a vanilla network, SDP on the network. Okay, all right. So now comes the model, right? And this is the part that I hope will change later, which I'll talk about at the end of all the slides. So the first part is just the block model. The second part now is very much like what we had before. So it's mean plus noise. The means are the same from every different cluster, like a mixture of Gaussians, but it's not Gaussian anymore, it's sub-Gaussian. So the WIs are mean 0 and sub-Gaussian. The problem with this is that D has to be high dimensional. So this is in fact very similar to, I think, Nuruddin El-Karoui's work from 2010. So the idea is that your mu does not have to, is very sparse. So your data is lying in a sparse, on a sparse manifold, and it's kind of obfuscated by high dimensional noise. Okay, so mu 0, even the distance between the two cluster centers do not have to grow as n is growing. In fact, it can shrink at a certain rate, as long as all the conditions are satisfied. Okay, so let's see. So here is kind of the consistency. It's like a big blob. So let me kind of walk you through the salient points of this. Forget about the first line altogether. The gamma, don't worry about it. That's like something like order the probability, it shows up because you have unbalanced clusters. So if I have a very small cluster with a very tiny p, then I have to somehow take that into account. Now, there are two cases. One case is when you have a sparse graph. The second case is when you have a dense graph, so degree is growing faster than log n. So let's look at the first case. So my pk and qk, remember pk is within block connection probability, qk is the largest of the outgoing probabilities. So in that case you can show that x hat minus x0, the L1 norm, is less than equal to epsilon times n. Now why is that a good thing? Well, remember that my x0 is this normalized thing right here. So if you look at the L1 norm of this, it's n. Okay, so whatever was in the denominator before, it's n. So epsilon really is a multiplicative error. And if you are wondering where is epsilon in the rest of that statement, epsilon in fact shows up in this sufficiently large bit. Okay, it shows up in the denominator, as you can imagine. So I can't have epsilon go to 0. I'll have it blow up essentially. So what do I have here? Let me first forget about the lambda altogether. It's min k pk minus qk, which is exactly kind of what I think Arash had. And the moment you see min k pk minus qk, you are talking about weakly assortative models, right? Because you are not looking at the smallest of the p minus the largest of the q's. So the nu k essentially is a huge thing that I don't want to talk about, but all you need to know is that it's a function of the minimum distance of the kth block, the kth mean, to everyone else. So if that distance is very large, then nu k is going to be very large. So it's kind of like the first part is the separation from the graph, the second part is the separation from the covariates. Similarly here, there is no consistency there, but here you can have consistency, and essentially this separation thingy turns up at the denominator. Okay, so if the separation is large, you have a small error. The separation is small, you have a very large error. Now, why is that interesting? So let's think about this. If these two were the same order, because lambda is not a constant, it's basically can depend on n. So if those two were the same order, that's basically saying that the graph and the network both are giving you the same amount of information. And what happens in that case is both are equivalent, both are consistent at the same rate, and all you get here is a constant times improvement in the error, which is not surprising. And if anyone, right, because if this one was twice that one, you are dividing the error by half by adding in the covariates essentially, constant times improvement. However, the most, I think, interesting thing happens when if you have a cluster K such that it is not actually separable in the graph space, so pk minus qk is very small, but this nu k is large because the means are well separated, then you can have consistency, whereas each one of the methods will fail. How much time do I have?
7.
Oh, okay, good. That's, I guess, what falls out of this, which is interesting, and that also falls out because of the weak assortativity, right? Because you are doing this in a much more minute level. You are not doing it by looking at all the blocks together. And what else do I want to say? Right, okay, so let me move on to the next slide. Are there questions? Sorry, I never asked. Questions, comments? Yeah, it's not a condition. You can.
Or it can be sparse. Does that mean that some covariates may have the exact same mean in all clusters? Or I'm just not sure what's the baseline.
It's possible that some of the covariates can have the same mean in the different clusters. Yes.
And some covariates
Are different.
have a different mean?
Yeah. Yeah, because that will come out from your nu k here. Because if it's same in all the covariates, then the nu k will be 0.
But
You won't have any separation from the covariates then.
so in practice, if you have like 2 covariates that are different and 100 covariates that are the same, what's going to happen?
That's a good point. I think that if we want to take that into account, we'll have to do something with the kernel. But right now, the kernel is a Gaussian kernel, right? E to the power minus the the thing. So yes, that's a great point actually. You are basically saying that it could drown the other points. Wait, but if all of them are the same, then it will just be 0, the distance there, these two.
There's noise, right?
Yeah, so
The mean is the same, but not
right, so essentially as long as the separation condition is satisfied, it will work, but yeah. Okay, so here are some plots, right? So, oh, this is not showing up very nicely, okay. So I'm basically plotting the NMIs, average NMIs box plots for those, and of course, Carl, I have picked out a situation where I beat you.
Yes, there's lots.
Well, because it's very unbalanced, that's why. We wanted an unbalanced situation. So this is just the network, this is regularized spectral clustering, this is the, with the covariates, this one is with the spectral method, and the final one is the combined one. And what do I have here? The first cluster is well separated in the graph, but has the same mean in the covariates. The second cluster is well separated in the covariates, has the same rows almost in the graph, and that's why each one of them will do really poorly. But if you put them together, you will get the right, get good results. To be totally honest, most of the time, for a lot of parameter settings in here, spectral clustering does well, but SDP does slightly better because SDP is kind of, you are really kind of have a big gun sort of. That's SDP, right? So what do I have here? Here I wanted to see where things are constant, not constant. So both the information from both sources were of the same order. So you have consistent methods. So if I combine both of them and I get a constant times improvement, what do I get? Right? And even here, I kind of the blue line is the combined one, the red one is the covariates, and you can see that they are kind of very close to each other because they both have roughly the same power to classify things. That's the NMI on the y-axis, and I'm basically varying the number of nodes on the x-axis. And you basically again see that it really does help to give you combine the covariates and the network.
Now, if all the mu's were the same,
Yeah,
the blue curve
will become the
a little bit worse than
Sorry.
that, right? It would be a little bit worse.
yes. I see what you are. That's absolutely
I
right
wonder
because
how
you are
much
tuning.
How much worse can it get?
Actually, it's not that much worse from my experience because what happens is the way you tune is you basically keep tuning. Tuning is a problem here, but the way you tune is you vary a bunch of parameters, you measure your similarity to the two sources, and when it crosses or when you, and in the case where one of them has all the information, it's very easy to catch that. So the tuning parameter finds the right spot pretty quickly, yeah. There might be noise, but I think it will be roughly the same. But that's a good point. Also, you can see that here the d is growing at n to the power 2/3. What would happen if I fixed d as say about like, I think I did it with d is equal to 200 or 300. What happens is covariates do really well and then flattens out, right? Because the high dimensional part is kind of necessary for kernels to basically concentrate around block structured matrices. And if that doesn't happen, and then even if it flattens out, it kind of, the combined method does pretty well. Okay, so let's move on quickly because I think I'm running out of time. Here is the Mexican politician network again. The first row I've already shown you. And in the second row, this one is the combined one. This one is the one with the network. This one is just kernel k-means by an SDP. So, and essentially you can basically see that all those nodes which are kind of confusing in one, because you have equal number of neighbors in both groups, for example, in the graph, and so the graph really messes them up. For example, those two arrows, they're messed up by the graph here, but there is some information in the covariates, so if you put them together, you actually can retrieve the labels of those. Okay. How much time then? 2 minutes, great. So I'm going to skip over Weddell-C, but kind of have nice results here. On most of we have a bunch of data sets. The two I'm seeing are ones I'm beating everyone else. But in general, what I would like to say is, in most data sets, if there is something to be said, if there is enough information, SDP, the combined often does as well or better, okay, because it's just, that's what I have been seeing. Even if it's heavily computational, it does kind of give you some advantage. Okay, so let's move on. Actually, this one, I will now say Dave here, but so here is kind of like a summary of all the things I like and dislike. Okay? So the first thing is the weakly assortative thing. It kind of came for free for the sparse setting, fine. The consistent estimation when one source doesn't have the information but the other does, that also is very crisp here, which is nice. And also the nice thing is that you don't have, both of the sources can have equal information. One of them doesn't have to go to 0. Oh, the third one is something that I didn't get time to talk about. It's robustness to outliers. So we have some theory, if I throw in outlier nodes, right, if it connects to everyone at random, for example, or in some other way, what we have been seeing, and we have tiny little proof for it, is that SDPs are better than spectral methods. They're both robust, but the SDPs are actually, you can actually see it in the error guarantees, that they're slightly more robust than just spectral methods. And if you plug in covariates, they're even more robust. So I think covariates will help very much for robustness. And what I don't like is the theory right now only works for high dimensional covariates. I don't like that. I hope, even if it's low dimensional signal plus high dimensional noise, hopefully we can do something about that. And when both are equally informative, you only get a constant factor improvement. I don't know if we can do anything about it, but that's all I got. And now SDPs can do, I think, assortative plus disortative if you blow up the graph size by n times k, so that will go. But are slow. No matter what you do for whatever models, they are very slow. So that's like Dave mentioned, you can use non-convex approximations, or somehow maybe in Showmendu's patch things up, you solve small SDPs and patch them up and solve, like, do a spectral clustering once, which is faster. You can do that. Yeah, that's it. Thank you.
Thank you. More questions or comments?
Okay.
I have a question. I find it strange too. You also mentioned Y only works for high dimensional covariates. That seems.
Yeah, because it doesn't concentrate. The kernel matrix won't concentrate if you have low dimensional
covariates to concentrate.
Yeah, so if you have a low dimensional, so I guess it's kind of natural, right? Because you have a low dimensional thing, then the information you're getting is n times d. From the graph, you have n square observations. And so one of them will always dominate the other. Hopefully, we can prove something else.
I mean, why don't you move the signal in the low dimension and let this low dimensional signal grow?
Yeah, so you will have to do something like that. You will have to have the distance between the means grow at a certain rate.
But that then gives you a realistic answer, because D having to grow is silly. It's not silly to say that signal has to grow.
No, but it's also true that if you have, I mean, often I don't believe that the means are growing as the number of nodes are growing too. That I think I can fold that in and have low dimensional methods, and we didn't do it because wasn't
You're
clear.
right, Noah. We don't want either signal or D to grow.
You kind of, because graphs are sparse, right? It's sparse graphs, you have P minus Q decay, not grow, hopefully.
Yeah.
You said SDP is more robust than spectral clustering. Did you see that in practice? Because in proof, it depends on how you prove it.
What do you mean depends on?
In simulations?
I saw it both in simulations and in the proof, yes. I mean, I don't have a lower bound, but I think I can have error bounds where one is much more sensitive to outliers. Because SDPs are giving you a denoised matrix, and so that will be always more robust to outliers.
So the
Yeah, please.
proof of Gordon and versioning, so they show that SDPs are sensitive to L1 infinity norm, which
Yeah.
is not, which if you just perturb one node a lot, so spectral norm would be affected a lot. So if I just add a very high degree node, then as Mark Newman was talking, about it, you end up that the eigenvector will be pulled toward that a lot more.
So,
Whereas this sort of puts uniform weight L1 infinity norm, so it just doesn't matter.
so the proof right now is just for the kernel, and the fact that adding covariates gives you a boost is in experiments.
Yes, that I'm not sure, but just the vanilla SDP itself would be, it seems like because of this might be robust to
Oh, I see, okay.
just that.
Yeah. Well, let's thank Purna again.